So this webinar is talking about whale corrugation suppression by tune mass damper. The content today, 6 types of corrugation. We found that there is many curve track have a corrugation noise of around 500 Hertz. Showing how the corrugation suppressions by the tune mass damper. Okay, then we would talk about a new theory, explain why the corrugation noise occurs around 500 Hertz and why the whale damper can effectively reduce the corrugation. We call it alternating triggering among the front and rear wheel. Then we can also have some animation on the whale damper, reduce the lateral mobility of the whale and absorb the whale vibration. Then at last, we talk about 2 different types of whale damper mounting for corrugation suppression. Most of the damper are focused on the vertical vibration, and also they are using the rubber layer interface. We develop a widget interface damper, which take care of vertical and lateral vibration, and have widget mounting to ensure the force transmit between the whale and the damper. What is corrugation? It is a wave-like wear deformation on the whale running surface. Slight corrugations, such as 5 micrometer, it causes very loud noise, although it has no impact on the train operation. But it increased the noise level by 15 dB, and making the undercar noise level higher than 110 dBA. A curved track is easier to have corrugations. We also found that resilient-based plate is also easier to have this type of corrugation around 500 Hertz. Environmental impact assessments normally are difficult to predict the corrugation location and depth. In most of the EIA, they assume such that corrugation would not develop too much. They allow a few dB, maybe 3 or 5 dB corrugations correction factor. Okay, this case we already played it last time. Oh, before we carry on, let us look at this graph. It is called spectrogram. The color represents the noise level. Red color is high noise level. High noise level. So this is location of high noise level. Location of high noise level. Green color is noise level lower. Then this axis is the time domain. The y-axis is the frequency. So this is around this corrugations. This noise level is around 460 Hertz. So let's carry on to here. Are you able to hear the noise? We can see that there is a F curve at the free run. At each turn, it has corrugation curve noise at around 500 Hertz. So the 6 type of corrugation. Heavy horn, light whale. The first 2 type is actually relating to the overload of the dynamic excitation. Such overload and making the plastic bending or plastic folds in the whale. And then the P2 resonance, wafting, pin-pin resonance, and chevron specific, total of 6 types of corrugations. In terms of the corrugation mechanism, we should notice there is 2 mechanisms. The first one is called the wavelength fixing mechanism. It makes the corrugation repeated at regular interval. Normally, it relates to some kind of check resonance or wheel set axis resonance. We will focus on the check resonance because we can control the whale vibration, control the check resonance by whale damper. Also, this is the major factor for the wavelength fixing mechanism. The second mechanism is damage mechanism. It's either sliding wear the material, just wear out the materials, or plastic deformation. In this seminar, we talk mostly about the sliding wear. So it just during the sliding, there is some material is removed. This is a summary of the 6 types of corrugations. The wavelength fixation mechanism relating to vesselings, P2 vesselings or second torsional vesselings of the driven axle, pin-pin vesselings or platform specific. Before we move on, we also need to notice there is 2 types of curving behavior. When the train running at high speed, there is a centrifugal force pushing the wheel outward towards the high wheel, such that both the front wheel and rear wheels touching the high wheel. Then the low wheel have lateral stick slip at both the front wheel and rear wheel. If the train travel at lower speed or at a sharp curve or at lower speed, then due to the gravitational force, the wheel set will be moved towards to the low wheel, such that the flange contact at the low wheel, like this. So flange rubbing at the rear wheel, and the lateral stick slip mostly happen at the front wheel inner wheel, the low wheel. There is a stick slip action when the wheel traveling along a curve, it accumulates the grip force until the grip force larger than the friction force. It have a slippage, and this slippage is have action and reaction force. They have the same magnitude. The force pushing the wheel is same as the force pushing the wheel. Then we will ask a question: which one has higher movement? The wheel has higher movement or the wheel has higher movement? Then we need to look at the mobility. This is the mobility of the wheel. It has high mobility at certain Westlands mode. -4 is already a very high mobility. At the 500 Hertz, at this one, compared to the wheel, we can see there is a pit have high mobility. This is due to the pin-pin resonance. Pin-pin resonance. In this wheel, the pin-pin resonance is 570 Hertz lateral mobility. What I mean pin-pin resonance is we measure the mobility at the midpoint of two support, two base plate, at the midpoint of two base plate. So this, when we hit the wheel there and measure the response, so this is the lateral mobility. At the midpoint, they have the pin-pin resonance, 570 Hertz. But at this point, the pin-pin resonance do not occur at this point. We can see that at the green line, at the support, the green line is at the support, there is no resonance. Then we can see there is another wheel head rotation resonance at around 480 Hertz. This rotation is creating the problem of corrugation. Both the midspan, the red line, and the green line is at the support. They have very high mobility there. So when the stick slip actions occur at around 500 Hertz, then the wheel low movement, almost low movement. But the wheel have very high movement. Other measurement on other wheel, in general, there is relatively high mobility in the wheel than in the wheel at this frequency. At this 500 to 400 to 700 Hertz, the mobility of the wheel is much higher than the wheel lateral mobility. Compared to the stick slip actions, the wheel is running forward and accumulate the grip force. Then until the grip force larger than the friction, it slide. When it slide, it remove some material. So it stick, slip, and remove material. Stick, slip, and remove material. There is different photographs showing this type of corrugation. Normally, they are only 10 micron or 20 micron. Is not very deep. Then we talk about 7 corrugation noise of around 500 hertz. This one we already talked about. In the side one, there is corrugation noise of 460 hertz. It is a UIC 60 whale on a resilient base plate of around 14 kilonewton per millimeter. Then the side 2 and side 3 is in Taipei, in Taiwan. They also have a frequency of 468, 452. So this very loud noise due to this corrugation. Then at the side 4 is wider in Hong Kong. They also have the 460 saloon noise at the 460 hertz. So all these sites have a corrugation noise at curve track with UIC 60 whale on resilient base plate less than 25 kilonewton per millimeter. The corrugation frequency is around 500 hertz because there is a high mobility of the whale at 500 hertz. It is independent to the train speed, independent of the train type, independent of the radius of curvature of the whale. Another site showing the corrugations. This is a LVT. We install damper on it. However, at this location, there is a whale joint. We could not install our damper there. Then the corrugation clearly coming out. And site 6 and site 7, we will detail present the corrugation data. This corrugation is at the site 6, it is around 315 hertz. It was in year 2011. In this site, we measure the corrugations, which is 313 hertz. With the damper, the corrugation there. Without the damper, the corrugations much higher after 7 months of grinding. We will further explain this. For the site 7, we have 2 corrugation frequencies. Sometimes it appears at the 528 hertz. The corrugation up to around 3.8 micron. Sometimes the corrugation frequency around 352 hertz. It up to 3.4 micron. Those dotted line is without damper. Solid line with damper. We will further explain in the later slide. Actually, in all our damper installation site, if it is installed at curve, we can see that they provide corrugation suppression visually. We can see there is less corrugation whenever the damper is installed there. Okay, then the last 2 cases, site 6 and site 7, we will further explain the data. This is the site 6. Without damper, the corrugation is clear. With damper, the corrugation is almost invisible. That is in year 2011. Nobody was expecting a whale damper can reduce corrugation. Then the track engineer called me and tell me they found that and asked us to do a corrugation measurement for 2 years. Then we conduct the whale roughness measurement, the corrugation measurement over a period of 2 years. It includes 4 grinding cycles. The corrugation measurement is quite simple with this unit. This is the result of the corrugation measurement. This is the time, November, December, January, February, until May, 6-7 months. Grinding was conducted on the 24th of November. The y-axis is the roughness micron or corrugation depth, RMS corrugation depth. Different color line represent different wavelength. For example, the red line is 80 millimeter with damper. With damper, the corrugation grows very slowly. The red line without damper, dotted line. The dotted line, the growth much faster. So we can see the corrugations increase very slowly. This is maybe the corrugations much faster without the damper. So then the bullseye is 63 millimeter. With damper, it go up to there. Without damper, it go up to there. If we measure the overall corrugations, including 10 mm, 12.5 millimeter, 16 millimeter, up to 160 millimeter, all corrugation together, they have a bed line. The bed line is like this, without damper. With damper, we can see that after the grinding, the roughness is not the best. It takes another month to achieve the best smooth wheel. The train operation actually smooth the wheel, make the wheel more smooth. This measurement is on the same wheel, just at the adjacent section. One section with damper, the adjacent section without damper. So it's a continuous wheel. Okay, this is the first side of the rigid damper installations. Corrugation suppression was not expected because the damper was designed just for noise reductions. From this graph, we observe that the corrugation growth is constant and independent of the corrugation depth. At that time, many engineers would assume the corrugation growth would be exponential growth. That means when the corrugation deeper, it go faster due to the dynamic reaction force with the corrugation. So at that time, many people think that the corrugation would go faster and faster, exponential growth. But from this data, we can see that most of the data showing constant growth. That means the corrugation damage mechanism does not depending on the corrugation depth. The corrugation depth would not increase the damage mechanism. After the 7 months, we grind the wheel and make it smooth again. Then we conduct the second cycle. However, in the second cycle, the grinding is stopped at the middle of the damper section. So the second section may not be a good reference because the wheel was not grinded a certain section. So then we have 3 cycles, grinding cycle 1, cycle 3, and cycle 4. This animation is showing that how the TMD, the tool mass damper, amplify the wheel oscillation, the wheel movement. The damper is around 5 to 8 times more than the wheel movement. And such the TMD movement creating a reaction force. The reaction force is always counteract the movement of the wheel. So this is the function of TMD. So a small mass can create a large force to counteract the wheel movement. This is the result of the 4 grinding cycle. We can see that with the damper, the bullseye is 80 millimeter wavelength. It increased to 2 micron, and after grinding, it reduced to 1.2 micron, then increased to 3 micron after grinding, and increased to 2 micron, and then grinding, and this quite smooth. The corrugation growth is very slowly with the damper. Without the damper, we can see that the bullseye is going up. After grinding, it go down there, up, down there, up, and down there, up. So in general, we achieve 70% of corrugation reduction. It was published in the 11th International Workshop on Railway Noise. Also, it published in the TDH Rail magazines in 2013. So this is the first reported case of the rail damper suppressed the corrugation growth. Okay, then this slide 7, we further explain this graph. It includes 3 grinding cycles with and without damper. The damper look like this. Okay, how the free gliding cycle? The data is average of 200 meter, average of 200 meter CAT data. The corrugation is 1 micron, 2 micron, 3 micron. The wavelength there is two critical wavelength. One is 31.5 millimeter, correspond to 528 hertz, and the other is 50 millimeter, corresponding to 332 hertz. The first two gliding cycle without damper. In the first gliding cycle, we measure the corrugation at 2nd month and 4th month. In the second gliding cycle, we measure the corrugations at 2nd month and 3rd month. First two cycles without damper. Then the first cycle after installation of damper, we conduct corrugation measurement in the 1st month, 2nd month, 3rd month, and 4th month. The result was also published in the ICSV 27 in 2021. It is 200 meter long whale damper installations. The base plate is a resilient base plate with the static stiffness is around 14 kilonewton per millimeter. Okay, the damper installation. At this site, the target is to reduce the noise level of 4 dB. So we are sure that we don't need to full installation the damper. So at the high whale, we only install 1 damper every 4 space because we found that most of the noise coming from the low whale. At the low whale, we install the damper. We can see that the damper is very small compared to the space. Actually, we can install 2 damper at each space or 3 damper with slight modification on the damper. So there is sufficient space to install 3 damper. If the client want to have higher damping, we can always add more damper. The tune mass damper was tuned to 550 Hz, both vertical and lateral. However, the damping is already covered from 400 Hz to 1200 Hz. It is single installation on the low whale, quarter installations at the high whale. With this arrangement, the saloon noise is already reduced 6 dB. In the first gliding cycle, at the 2nd month, this is the corrugation level. At the 31.5 millimeter corrugations, there is around 6 dB. 6 dB. Then to the 4th month, it increased to 12 dB. So there is, without the damper, the corrugation increased significantly. Then the 2nd cycle, it also increased from there to there. With the damper, that is the 1st month, the green line is the 1st month, the red line 2nd month, red line 3rd month, and the blue line is the 4th month. We can see that the growth is very slow with the damper, although it's still exceeding the TSI limit. We can compare with the damper, 4-month growth is from the green line to the blue line, growing very slow. Without the damper, the growing is very fast. This graph is in exponential scale, in dB, in exponential scale. We change it back to the linear scale, such that this is not dB, this is the micron. Then we change back to the linear scale. We can see that the growth is from around 1.2 micron increased to 1.6 micron from the 1st month to the 4th month. However, without the damper, the corrugation growth is from 1.3 micron increased to the 2.4 micron, or from this 1.9 micron increased to 3.8 micron. If we plot the data in according to time, so this 30 days, 60 days, 1 month, 90 days, 3 months, 120 days, 4 months, then we can see the growth rate of this 31.5 millimeter corrugation. In the first grinding cycle, we measure the corrugation there and measure the corrugation there. It can see the growth rate is around 1.26 micron per month without damper. In the second cycle, we measure the corrugation there, and the corrugations is around 1 micron per month. After install the damper, we measure the corrugations in the first month, second month, third month, and fourth month. It is very slow growing. The growth rate is 0.12 micron per month. So the reduction is around 90% growth rate for average of over 200 meters. If we look at the corrugation data, every 20 meters from the shrinkage line 20 to line 140, line 140 to line 160. So different shrinkage altogether is 200 meters. So every 20 meters, there is the corrugation reduction. Most of them achieve 95% corrugation reduction. At certain occasion, because the corrugation growth is not very high, the reduction is 89% or 88%. Talking about the mobility, the vertical mobility, this is first harmonic of the entire wheel bouncing up and down on the resilient base plate. Once with the loading, with the wheel loading, this would become the P2 resonance, and it would move to 60 Hertz or 50 Hertz. So we do not talking about this. This is also create a lot of problem. It may create very low frequency noise or ground bar noise. This is the vertical pin-pin resonance at 1030 Hertz. The mobility is just larger than -5. This mobility, the vertical mobility, vertical pin-pin resonance, create some problem. Many sites have a high noise level due to this vertical pin-pin resonance. But compared to the lateral mobility, the lateral mobility is 10 times, 20 times higher than the vertical mobility. That is more than 20 dB higher than the vertical mobility. So if there is repeated stick-slip action at this frequency, it will create the wheel vibration, very high wheel vibration, and stick-slip remove the material from the wheel and cause the making the corrugations, the pin-pin resonance, and the wheel head rotation. We try to establish a theory. The concept is very simple. It is alternating triggering among the front and rear wheel. According to the 6 type of corrugation, this type of corrugation should be an example of the 6 type of corrugations. The shearing triggering between the front and rear wheel mainly occur at the low wheel, sometimes at the high wheel. The frequency is majorly at around 500 Hertz. Corrugation frequency is quite easy to calculate. The frequency is equal to the shear wave speed in the wheels divided by 2 times of the wheelbase. Okay, let's see some animation. The train is going on this way. So the wheel would going front, forward, and then slide, and going forward to accumulate the lateral grip force, and then slide, going and then slide. When it slide, it creating action and reaction force. The action force making the wheel vibrate a lot because the wheel has high mobility at the 500 Hertz. So just recap this stick-slip actions. This stick-slip action in this case is occur at 500 Hertz. It make the wheel have a very high vibration. And this is animations. It create the wave, this wave, when it arrive the adjacent wheel, it trigger the slippage. Because before the wave arrive, this wheel is already accumulate a lateral grip force. It already very close to the slippage. This Kip force is already close to the maximum friction force. So once there is some shearing wave trigger, it would create trigger it to slippage. In many cases, the wheelbase is around 2.5 meter, and the wave along the shear wave along the wheel is around 2,600 meter per second. So it takes around 1 millisecond go from the front wheel, and then around another 1 millisecond going back. When it go back, the wheel is already moved 25 millimeter or 35 millimeter. So it already moved. So the wave going there and coming back, it already going there and then going there and come back and going there and come back and create a repeated pattern. Slippage is both towards to the low wheel. In some case, the rear wheel would be slipping to the high wheel, depending on the speed. And there is two cases of the curving behavior. The rear wheel is sometimes slipping downward or slipping upward. So in this case, the Kip force is different. This one is the wheel is moving outside and then sliding towards inside. This wheel is moving inside when it travels, and once the wave trigger is sliding outside. So there is two different cases of sliding, but they are both triggered by this shearing wave. If we put a wheel damper, because the wheel mobility is already decreased, making it very rigid, it decreased the mobility. So when there is a slippage, the wheel movement may be similar to the wheel movement. The wheel move is very small. The amplitude is very small. Also, along the traveling path, the damper absorbs the vibration. So when the vibration arrives to the adjacent wheel, it's already reduced to a very small amplitude. It cannot trigger the slippage. This hypothesis to explain why at many curve shaft they have around 500 Hertz corrugations, and such corrugation can be very easily suppressed by the wheel damper. Then we talk about the wheel damper mounting type for corrugation suppression. The typical wheel damper, the design concept is maximize the contact area. So the wheel damper designed to have contact area all along the profile of the wheel. So this allow they capture more vibration energy. However, in the real situations, the rubber is only touched at certain points, For example, if they decide when the wheel damper touch the wheel have, for example, have a 5,000 millimeter square, just 5,000 millimeter square touching area. However, in real case, they only touch at a few points. They only touch at maybe 100 millimeter square. The design stiffness was based on a large touching area, but in the actual case, they only touch a small area. The interface become very soft. When a soft interface, it would act as isolation. So the wheel vibration, most of the wheel vibration energy would stay in the wheel, only a little bit energy would be transferred into the damper. This problem is due to the rusting, due to the painting, or due to the extruded works in the wheel. So when the wheel damper retrofit into the wheel, although they have very good data in the laboratory or in the test track, but once retrofit, they found that the performance is much less than they anticipated. Based on this, we developed the rigid contact wheel damper. It has 3-point contact and with the metal to metal contact, ensure there is high rigidity, very rigid, very stiff, such that even 1 micron or atomic level vibration. It also can absorb. So because it has rigid contact to ensure the transmission vibration into display, and then the oscillator amplify the movement to create a counteractive force to counteract the wave movement. So it has only 3-point contact. It do not maximize the contact area. Ensure this coupling, a perfect coupling. So the coupling loss is zero, nearly zero. And also it allow the track inspection, visual track inspection easily, because it only have a 3-point contact. Most of the wheel surface can be visually tracked. This oscillator will amplify the wheel vibration by around 8 times, and these oscillations would create a counteractive force, always counteract the movement of the wheel. So with a small mass, it creates a very strong damping. This is the concept of the tune mass damping. This is the end of my presentation. Thank you.